Welcome to qnawire.
Hi, so over here we're going to review what is going to be orbital hybridization of the carbon atom. So, in order to do so, let's review the electronic structure corresponding to the carbon atom. We're going to have 1s2, 2s2, and the 2p orbitals, in which we're going to have only 2 electrons. Remember that carbon is going to have a balance equal to 6, so this would be the electron configuration for the ground state. However, in order to form 4 bonds in a tetrahedral arrangement, what is going to occur is that we can consider an excited state in which we're going to transfer this electron, let me put it in purple, this electron over here towards one of the p orbitals, generating the configuration 1s2 and the other ones 2s1, 2p3. Notice that under this arrangement, what can occur is that the extra electrons coming from the hydrogen atom can enter into the configuration 1, 2, 3, and 4, fulfilling the octet. In this case, what allows the combination of the atomic orbitals is going to be the geometry. So, whatever the geometry we're going to have, this is going to be the one responsible for the combination of atomic orbitals. In this case, since we're combining one s orbital with 3p orbitals, what is going to be called these combined orbitals are going to be named sp3 orbitals. That are combinations of the 2s orbital and the 3 different 2p orbitals, 2px, 2py, and 2pz orbitals. And these mixed orbitals are going to have the corresponding space for that sp3 orbitals. We're going to have 4 of them. Now, for the other type of hybridization, they're going to come also from the same initial. Oh, sorry, before we continue, due to the geometry that we're going to have, the angle in between all of them is going to be of 109.7 degrees, corresponding to that of a tetrahedral, or 109.5 degrees, something around that. Next up, we're going to have sp2 orbitals, in which the 2s and the 3 2p orbitals are going to be combined in a different fashion. The number of orbitals is going to be the same, but now for sp2 orbitals, what is going to occur is that the ones that are going to be combined are going to be only 2 of the p orbitals. This is due to the trigonal planar geometry that we're going to have under these conditions. These sp2 orbitals are going to have the same energy. We're going to have 3 of them. And we're going to have on its own the 2pz orbital. In this case, the electron arrangement would be the following. Again, we're going to have 3 single ones over here and a single p-set orbital staying on that position. Now, what is going to be the shape of these orbitals? Well, what we are going to happen is that in between the two carbon atoms, I'm going to write down the sp2 orbitals in purple, and they're going to be essentially the ones responsible for the sigma bonds that we're going to have under this arrangement. Let's say that we have an hydrogen over here that overlaps, another hydrogen over here that overlaps, another hydrogen over here overlapping, and another hydrogen over here that is also going to be overlapping through s orbitals. All of these are going to be sigma bonds responsible, but which are going to be generated by the sp2 orbitals that we're going to have. But in addition to that, we are also going to have the 2p set orbital on each of the carbon atoms, which is going to be perpendicular and responsible for the pi bond over here, generating the double bond in between the carbon atoms. So this compound would generate the double bond over here, carbon-carbon, hydrogen, 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 and hydrogen. Remember that over here we have one sigma bond and one pi bond responsible for this type of interaction. And now going for the last one, the sp type orbital. This is going to come from a linear arrangement or a linear molecular geometry, which is going to allow to interact the 2s orbital with one of the 2p orbitals that we're going to have. Let's label the one that is going to be interacting 2px. And we're going to have the 2py and 2pz on their own. The only ones that are going to combine are the two over here, generating the sp-type orbital. How many of them? We're going to have 2 sp orbitals per carbon atom, and the other two are going to be free. In this case, for a linear arrangement, let's say that we have our carbon and hydrogens as such, the sp orbitals I'm going to write it down in purple, are going to be responsible for the sigma bonds in between carbon and hydrogens for this overlap, and the 2py and 2pz orbitals, which I'm going to write down in green, are going to be responsible for the two additional pi bonds. We're going to have the 2pz interaction over here, generating a pi bond. The purple one is going to be a sigma bond. And additionally, we're going to have the 2py orbital. I'm going to put it in black, which is going to be perpendicular. And that would generate the extra pi bond. So overall, in between the carbon atoms, we're going to have 2 pi bonds and a sigma bond, generating the known triple bond that we have seen in organic chemistry. And with that, it would be all. Remember that whenever we have this type of interactions of hybridizations, they are going to be given by the combination of atomic orbitals allowed by the geometry that we're going to have. For sp3 orbitals, we're going to have a tetrahedral arrangement. For sp2, trigonal planar arrangement. And for sp, we're going to have a linear arrangement of the atoms. And with that, it would be all. Thank you very much and have a good one.